So the interaction of organisms with the living and non-living, which we've talked about, parts of their environment cause their populations to change over time. Living things are what? Biotic factors, and non-living are abiotic. Right, very good. So there are some characteristics of populations that we need to be familiar with. They include geographic distribution, density, and growth rate. And we're going to talk about each of these individually. So geographic distribution of a population has to do with how individuals are spread out in a particular space or area. So they can be clumped, like you see up here. They can be random, by chance, or they can be uniform. So if we had somebody in every other seat or every seat, okay, that would be uniform. So clumped, random, or uniform. When we're talking about population density, we're talking about the number of individuals per unit area. So what do you see up on the board in the two pictures? Okay, so you see a whole lot here, and then you see them, well, I guess you could say spaced out over there, but really there's only what? One bear. So over here, many individuals in one area, that is considered a high population density. And then on the right, if there are fewer individuals in a particular area, that is considered to be a low population density. And then one of the last things, which is growth rate. Okay, a population can grow when its birth rate is greater than its death rate. So if you look up here, during which time period was this population growing? Say what? So it goes by 82, 84, 86, 88, 90, 92, 94. Say what? Okay, so you see kind of starts to increase here, right? But it also increases at the very beginning. Okay. What happens to a population if the birth rate equals the death rate? It's balanced, nothing would happen, right? Okay. And then what would happen when the death rate of a population is greater than its birth rate? Okay, eventually can. So what is going to happen to the population now? It's going to decrease, right? So there are two types of curves, growth curves, that we have to be familiar with: exponential and logistic. So exponential growth occurs under ideal conditions with unlimited resources. So this takes what is known as a J shape. So exponential growth is a J-shaped curve. So individuals reproduce at a constant rate here. So it's J-shaped, so it continuously goes up. It continuously increases. So a great example of this is bacteria. Okay, so bacteria grow under ideal conditions in a lab setting, okay? And they, in turn, grow exponentially. You can see over time, we start with one, and then they quickly multiply over time. The next one is logistic growth. So exponential is a J shape, and logistic growth takes an S shape, okay? So this occurs when a population's growth rate reaches 0 as resources become less available. And this typically follows a period of exponential growth, because if you look at the graph here, it starts off as a J, But then what happens is it reaches what is known as a carrying capacity. Does anybody know what a carrying capacity is?
Like,
Okay. Well, what does it mean? I don't know what it means.
like it's to a point where the environment is not enough resources.
Okay. So we can only hold so much, right? Okay. So logistic growth has that carrying capacity. So exponential, unlimited resources, but in logistic, it is going to be limited. So obviously, what y'all just told me, the population reaches a carrying capacity. And when they do, that is when the largest number of individuals that a given environment can support based on resources. So what can happen, though, as a population overshoots its carrying capacity, it can start to fluctuate, okay? So crashes are common as the environment can no longer support the actual population. So once it reaches the carrying capacity, if it overshoots, right, we have too many, so what's gonna happen? It's gonna have to decrease because people are going to, okay? And then eventually we can reach our carrying capacity again, but if it happens to overshoot again, the same thing is going to happen. So it's going to be like a check and balance, okay? So rapid life history pattern, organisms in an unpredictable environment. These are two different types of population growth here. So for example, mosquitoes, so we're talking about rapid life versus long life history. So mosquitoes have a small body size, they mature quickly, reproduce early, and they have a very short lifespan. So the population fluctuates rapidly depending upon specific conditions. Long life history pattern organisms live in stable environments. So like us, elephants, they're large, mature, they reproduce much slower, and then obviously we have a much longer lifespan, okay? So this is a population size near carrying capacity. All right, tell me exponential or logistic. Population increases indefinitely. Exponential. Population increases rapidly at first and then it flattens out. Logistic, that's right. Occurs as resources become less available. Occurs under ideal conditions. Exponential. Occurs when birth rate is greater than the death rate. Occurs when the birth rate and death rate are equal. Occurs when an ecosystem's carrying capacity is reached. Elephants have no natural predators except for humans. Describe the population growth of elephants after they are protected from hunting. Workers at Chipotle often leave out raw chicken for several hours at room temperature. Describe the growth of the salmonella on the chicken. All right. So now we're going to get into what actually causes population growth to decrease. These are known as limiting factors. Okay, so limiting factors are things that limit a population's growth. There are two types: density dependent and density independent. And just looking at those words, we should figure out what they mean, be able to figure out what they mean. So if you're independent, what does that mean? By yourself, okay? And if you're dependent, you need help. You're relying on someone else or multiple, okay? So density dependent limiting factors depend on the population size. So they depend on the size. And they have a greater effect on populations with greater densities. So obviously, the more there is, the greater effect it's going to have. So some examples of density dependent limiting factors are predation and competition, parasitism, and disease. So these all depend on the population size. So obviously, the more there is, like if a plague were to come, right? If there's more people, it's obviously going to affect more people. So we're going to talk about, before we jump into the independent piece, we're going to talk about predator-prey relationship cycles. Okay, a great example of this is the lynx and the rabbit, and I'm going to pull that up shortly. But we should know the effects of competition and of crowding and stress. So the effects of competition, so if the population is low, resources are plentiful, there are no problems. As the population increases, the resources will become limited, and therefore, if the resources are limited, then competition is going to occur, and it will increase. Effects of crowding and stress. If there's overcrowding, there's going to lead to stress. So individuals then become more aggressive, they show less parental care, and then in turn, there is decreased fertility. So up here is a graph, predator-prey graph of lynx and a hare. What can you tell me by looking at this graph? What do you notice? The lynx is blue and the hare is red.
The lynx decreases, the hare increases.
Say what you, I heard what you said. What did you say?
Hare increases.
Okay, immediately? Okay, so what happens in a predator-prey relationship, it's a constant cycle. So if we were to have the lynx and the hare, right? If the hares increased, then the lynx will increase as well. But there is what is known as a lag time in between, so it doesn't happen immediately. But if the lynx increase now because the hares increase, what's eventually going to happen to the hare? They're going to decrease, right? So then if they decrease, what's then going to happen? Then the lynx are going to decrease. And it's an ongoing cycle. So one increases, the other increases, one decreases, the other decreases. But you have to understand that there is a lag time in between the two. So it doesn't happen immediately.
So you said one decrease and the other increase?
No, one decrease, the other
So
decrease.
what if the lynx decrease with hare?
That's the cycle part. Yes. So like I said, if the hare increases, the lynx can increase, right? But then eventually, because the lynx increase, the hare now will decrease, which causes the lynx to decrease. And then it's going to keep shifting back and forth. Does that make sense? Okay. So we just went over. So the whole purpose of predation is to regulate the population size of prey, and the prey population regulates the population size of the predator. So they kind of balance each other out. Okay, the next piece is density independent factors. Okay, so these are obviously, they affect all populations in similar ways regardless of the size, because it is independent of the population size. So some examples of this are natural disasters, unusual weather, fires, and human impacts. Okay, so it doesn't matter what the population size is. If a tornado is coming, a tornado is coming, right? Okay, so that's the difference between dependent versus independent. So dependent relies on the population size, independent does not. So one of the last things that I'm going to talk about is human population growth. What kind of curve do we have? exponential. So there's what is known as demography. This is the study of human population growth characteristics. And demographers, they study the population growth rate. They study age structure, which I'm going to show you some of these, and geographical distribution. So human population has increased exponentially. We just saw that on the J-shaped curve, right? And therefore, humans are able to reduce environmental effects. So we've already talked about this, birth rates, death rates. So slow population growth rate if deaths exceed births, and there's a fast population growth rate if births exceed deaths. So does age affect population growth? And this is where we're going to get into some graphing. So a population with more young than there is old people will grow faster than the opposite. So if there is a population with more old people than young people, it's going to be the reverse. Does that make sense? Correct. Okay. So there is what is known as age structure, and this is shown on graphs that are going to come up here, and it helps predict the growth rate of a specific population. And you can pull these up and see these for all of the countries of the world. Okay, so if there's a broader base, when we're talking about an age structure graph, then it has a faster population that is increasing. And you'll see this on these slides. So this is what an age structure graph looks like. Has anybody ever seen one of these? Yes? Okay. So up here, this one is Germany, Mexico, and the United States. So if you were to look at these different graphs, this one is most stable. This one has a rapid growth because what did we say about the base? What did we say on the previous slide about the base? Is wider, broader, right? So therefore, rapid growth. And then this one in the United States actually shows a slower growth because we said that this would be true of the reverse. Okay, so if you were to look at one of these graphs, you need to be able to determine whether it is stable, growing rapidly, or growing at a slower rate.